Hello everyone, welcome back to Deterministic Optimization. We'll continue our discussion on decision making under uncertainty. In this lesson, we'll see some concrete examples. The learning objective for this lesson is, first, we're going to introduce a way to represent uncertainty, a picture way to represent uncertainty called scenario tree. And using scenario tree is very easy and intuitive to see what uncertainty means. And what decision or the two-state decision structure means. And then we'll solve a concrete example of the two-state stochastic program based on the stochastic inventory problem we introduced in the earlier lecture. And then we'll analyze the results. All right, here again is our stochastic inventory control problem. The problem's key structure is the two-stage decision structure. This is to model the situation where the production quantity, which is so-called here and now decision, has to be made before uncertainty is realized. So has to be made under uncertainty. And then some other decisions, selling decisions or discount selling decisions, these decisions can be made after the demand is realized. It doesn't have to be committed right now. So you can wait and see what the demand is and then decide. So this decision is called wait and see decision, and this is called second stage decision. So we formulate this stochastic program where the blue problem is the first stage problem, or sort of master problem, that the key decision to the company right now is the production quantity. So this Q should be X, and this V to match us should be Z here. This is the first stage problem. And then within the first stage problem, the second stage decision determines the future cost, or in fact the future revenue, or the negative of the revenue as a future cost. And that future cost is determined by a minimization problem, because the company still, after the company sees the demand and after the production quantity is fixed, the company wants to make as much revenue as possible or minimize the cost. So that's the second stage problem. So the key, again, the key problem structure is this two-stage problem. We have a first stage decision, and then we have uncertainty D. The first stage decision is made before D is known exactly. And then after D is known exactly, the second stage decision, where the Y's and the Z's are determined, are made after D is known. So here in the second stage problem here, D is a parameter that is known. So that's the key structure. And to represent this key structure, we introduce the so-called scenario tree. So suppose demand is a discrete random variable, which is the practical case and is the only case that we can actually computationally solve it. So here is the scenario tree. We have a grain point, a grain node here, matching the grain problem in the previous slide. This represents the first stage problem with the first stage decision variable X. And this problem here with this decision is made before demand is realized. But after X decision is made, we'll have different scenarios of the demand. So in this case, demand D is discrete random variable with S scenarios. So we have scenario 1, scenario 2, up to scenario S for the demand in the future. So each node here represents a specific demand scenario. So this S scenario here composed of the second stage problem. And at each node in the second stage, internally, the orange problem is to solve a minimal future cost problem to decide what is the second stage variable, y1 and z1, for that specific, for example, the first scenario, and what's the minimum revenue for the second scenario, y2, z2 for the second scenario, d2, and so on. And these variables, y1, z1, y2, z2, up to ys and zs. These are called nodal variables because they really are embedded in each node of the second stage problem, right? So this is just a pictured way to represent the relation between the first stage and the second stage problem. It's called scenario tree. And you can also imagine what if there a third stage. For example, from scenario 1 here, there are other possibilities for future demand. So the scenario tree can be actually extended to multiple stages. But here we just focus on two-stage problem. So here's a concrete example. Suppose the demand in the inventory control problem can only take 3 scenarios. The forecasting department tells us either demand is low, which is 10 units, or normal, which is 30 units, or high at 50 units, and with probability 1/4 for the low demand, 5/12 of the normal demand, or 1/3 of the high demand. So these are some forecasted probability and forecasted level of future demand. So the demand is a discrete random variable. And we also have some concrete numbers for the unit cost. This production cost is 5. And retail price at the regular price level is $10, for example, or 10 units of price. Or discounted price is at 3 units of price. So notice that the discounted price is actually lower than unit cost. So if there are overproduction, then the leftover of the product has to be sold at a loss. But it is still better than not selling it. So the production capacity, or how much can be produced, the upper bound is 70. So this is the two-stage problem with all these numbers. We have first stage cost plus here is the expected future cost, right? And expectation is taken over the probability distribution of the demand, which has 3 scenarios. The first is 1/4 of the low demand scenario, and this is the future cost, -10 retail price times how many to sell at the regular price given scenario 1 minus how many to sell at the discounted price for scenario 1. This is the expected, this is the part of the expected future cost for scenario 1. And so for these other 2 scenarios, 5/12 times scenario 2's future cost and 1/3 times scenario 3's future cost. And we have constraint on the first stage decision not exceeding capacity, production capacity. And each y's should not exceed the demand, all right? How many we sell at the regular price cannot be more than the demand. So for the scenario 1, demand is 10, scenario 2, 30, scenario 3, 50. And then for each scenario, we have this constraint, meaning the total sale cannot be more than the total production, and then non-negativity. So again, this is the implementation of the two-stage stochastic problem. Okay, and you see that this is a linear program. So let's solve the problem. So because this is a linear program, again, we can solve this using CVX, for example. I implemented this in CVX, and here are the results. So given the cost and the price parameters, as we discussed, 5 for cost, 10 for regular price, 3 for savage price, and these are the results. So the first stage optimal decision is to produce 50 units. And then for the second stage, wait and see decisions, if the demand is low, meaning 10 units, then we'll sell 10 units at the regular price because that's all the demand that there is. And then whatever is left is 40 units will be sold at a discounted price. For the normal demand level is 30. That's what we sell to maximize the revenue, plus whatever left will be sold at 20 units at the discounted price. And then for the third scenario, we have 50 demand. So that's a high demand scenario. All the production is sold, and there's no leftover. So this, given this price structure, this is the optimal way to do the production and selling. What about some other scenarios? For example, if the cost of Savage is reduced to $2, okay, it's less than 3. So if the Savage is less valuable, does that change our decision given the same demand distribution? And the answer is actually yes. So if the Savage is less valuable, our production will be also lowered at 30 unit. And all the demand will be satisfied. The only difference is we'll have less Savage sales because the Savage is very cheap. So we don't want to sell at a loss. So we see that the problem optimal decision actually depend on the ratio of the difference between the normal price and the cost, basically how much markup will sell, divided by how much the difference between the normal price and the Savage price. Okay, so the lower the Savage price is, also the production quantity will be lower. So this is some kind of sensitivity analysis for our problem. Okay, let's summarize. We introduced a graphical representation of uncertainty, meaning scenario tree, to represent uncertainty evolution and also represent the two-stage decision structure. And we solved a concrete example of a two-stage stochastic inventory control problem. And we analyzed the solution and analyzed its dependence on key parameters. Thank you.